Presenting today XRP Ledger Proof of Payment, or xPoP, which is a pretty cool little bit of tech we wrote, and it solves a very specific problem. So let's go straight to slide 2. Okay, so the problem is there's 15 million vending machines in the world and untold parking meters and Internet of Things devices and so on and so forth. And most of them don't have a connection to the internet. So wouldn't it be really nice if we could pay for something via the XRP Ledger and then prove that we paid for it to an offline device? So that's the basic crux of the problem that we're trying to solve. So we need to prove a payment was successfully made without both sides being connected to the internet. We know that users, customers have mobile devices, and they, generally speaking, are well connected to the internet these days. But the other side may not be. So the solution we came up with is based on the way the structure of the XRP Ledger itself. So on the XRP Ledger, you have validators. Validators sign validation messages. Validation messages contain a ledger header. The ledger header contains a transaction root. Transaction root is the root of a Merkle tree, and the Merkle tree contains ultimately the transaction blob and the metadata, which confirms that the transaction was successfully executed, and, for example, how many drops were delivered or any other information about the transaction that isn't the transaction itself. So with this chain of trust that we're exploiting here, you are effectively trusting that the XRP Ledger Foundation will not sign a validator list containing validators who will conspire to defraud specifically you. So that's the additional trust that you have. Other than that, it's the trust requirements are minimal because you have public key signatures and cryptographically secure hashes all the way down. Next slide, please. So the problem with this chain of trust is proving that all of that happened, proving that chain from end to end ends up being quite a lot of data. We have the full validator list needs to be included with the signatures. The validation messages for the ledger that the transaction ended up in needs to be included, and those validation messages can be quite large if it was a voting ledger. The ledger header needs to be included, the Merkle proof, so from the transaction root down the Merkle tree, all the way down to the transaction itself, which also needs to be included, and the metadata for the transaction. And when we sum all of that up, it's about 50 kilobytes. And I'll ask Vitsa now to just go to LiveNet and pick a random transaction, and we can show exactly how much data that we're talking about that we need to transfer to the offline device. Yeah, so if you scroll down here, this is the full validator list. It has all the validation messages, it has the ledger header, it has the Merkle proof, it has the transaction and the metadata, all for a specific, just random transaction that we picked off LiveNet there. So how do we transfer this? We've got the way that we want to do the chain of proof, but how on earth do we transfer it to an offline device? That's an engineering problem in and of itself, quite a difficult one. So next slide, please. Oh, it's not animating. It didn't come up. I'm not seeing it on my screen. You can you just pull the JSON off the end of the URL you just had before. Oh, there it is. We got it. Okay, cool. Yeah, so the solution that we came up with is animating QR codes, which look kind of funky, but they also look kind of cool. And what we ended up doing is we first broadly compressed our JSON, and then we base 58 encoded it so that we could use the text mode of QR codes. And then we split it into multiple QR codes, and we added some parity frames, and then we generated it as an animated GIF. And then we display the GIF, and this actually turns out to be quite robust. And so you can display this on your phone and cause the vending machine to receive that entire 50 kilobyte payload in about 10 to 15 seconds, fairly reliably. And then it can verify for itself that the proof is correct, and then vend your goods. Next slide, please. So why animating QR codes? Well, cameras are cheap. Cameras require no licenses, unlike potentially like a radio frequency solution. Phone screens are high definition these days, so we can have quite a dense QR field there. QR codes are familiar to users, so it's not like we're asking them to do something that's really strange and unfamiliar. They're just loading up a funky-looking QR code and displaying it back to the vending machine. It works even in noisy and crowded environments, so it'll work at a conference or a show or whatever. And it also works in electrically noisy environments because as long as you can transmit light, it'll work. Next slide, please. So we did face some problems in designing this. The refresh rate between the camera, so how often the camera takes an image, and the screen that you're viewing, so in this case your phone screen, they never match up. No, the chances of them matching up are almost zero. And the problem is, you might have seen this way back in the day when people used to film CRT screens, as shown in this picture here of this bowling screen. The rolling black bars. So this is where the frame doesn't match between the image that's captured on the camera and the image that's being displayed on the screen. So for example, the camera might catch at 60 frames a second and the screen might display at 24 frames a second. And those will always be out of sync and you're always going to lose some frames. So in the end, we decided we would add parity frames quite aggressively so that the camera only needs any 3 out of each 4 frames to successfully decode. And the parity frames work even a little bit better than that because you can, if you've got a lot of frames from early on, then you can decode, you can use some of the parity frames later on. Anyway, we will show you, we will link the code and you can have a look at it if you're interested. Next slide, please. So there are some possible attack vectors for this xPoP solution. The main one is a replay attack. So how does the machine know if you haven't already displayed this xPoP to, for example, another vending machine right beside it to prove that you already bought a Coke, and then this second vending machine also dispenses a Coke? But it's easily mitigated. You just place a random nonce into the payment request that the user is actually responding to. So the user will scan a QR code off the vending machine, they'll pay to that QR code, and then they'll generate the xPoP and they'll display the xPoP back to the vending machine. And as long as that random nonce is always different, which is very easy to do, then the possibility of replay attacks is down to the collision between the nonces, which is astronomically small. So next slide, please. So there are some additional issues. Obviously, the animated QR is only a one-way transfer. The vending device needs a timeout, so it can't just wait forever for the user to display the animating QR code. And it's possible that the user ends up paying, and the nonce times out, and then they just won't get their purchase. However, these are all the same problems that are currently faced by vending machines. You put your coins in, and it doesn't vend, or the little spiral thing comes out only halfway, or whatever. And you know, this is why vending machines have phone numbers on the side, so we don't actually see this as a big deal. Okay, it's demo time. So this is what you've been waiting for. Beats is going to make a payment. He's going to scan the QR code on his little vending machine there. So he's just setting it up with a random nonce. And there's the QR code to scan to make the payment. There he is, scanning in some. And now he's going to make the payment on the XRP Ledger. Now this vending machine is offline. It doesn't have internet connectivity. Yeah, okay, so the payment's gone through successfully. Now he's going to load up the xPoP for that payment. So you can load an xPoP for any payment or any transaction type on the XRP Ledger. Okay, now he's displaying it to the vending machine. And it should read the frames, probably decode some parity frames. And I assume it's vending. I can't I can't see. It's okay. Everybody's applauding. I can't hear you. I'm sorry, guys. So interestingly, I have just a couple more comments on it. Interestingly enough, this can actually be used with any XRP Ledger transaction type. And because it includes the metadata, you could even use it with a hook. So after a hook's finished executing, it has a return code and a return string that's stored in the metadata on the XRP ledger, and that would actually end up inside the xPoP. And so you could actually do a complete vending machine management inside the state of a hook and have basically the transaction accepted or rejected based on your known inventory, which is stored on the ledger inside the hook state. And then the machine would vend based on the metadata and the result of the transaction.